Okay, so I like to address the question on the blackboard. What is the rank of a matrix? And this is in the setting of the tropical semiring, of course. So suppose M is a matrix with entries that are real numbers, maybe infinity, with tropical arithmetic. So I'm going to say M has tropical rank 1, or just rank 1. If it's the product of a column vector times a row vector. So rank 1, that's unambiguous. It's very clear what we mean by rank 1. Same for tensors. I mean, rank 1 just means sort of completely independent. So for example, just to make sure, 2, 3, 5. So we have a column vector times a row vector, minus 1, 7, 0, 4. So then we get a product, 1, 9, 2, 6. In the first row, we multiply by 1. We get 2, 10, 3, 7. And then we multiply by 2. We get 4, 12, 5, 9. So this is a typical, it's a rank 1 matrix. Okay? It's a product of a column vector times a row vector. Let me give you 3 definitions of rank. Of the rank of a matrix. So the first definition, I'm going to call that the Barvinok rank. The Barvinok rank of M is the smallest positive integer such that M can be written is a tropical sum of rank 1 matrix of R, sum of R rank 1 matrices. Okay? So I'm going to say a matrix has Barvinov rank R if I can write it as a sum, tropical sum of R matrices of rank 1, but I cannot write it as a sum of R minus 1 matrices of rank 1. Now this is named after Barvinok. Barvinok is a mathematician interested in discrete math and optimization. And he used this notion of rank in a result on complexity theory concerning the traveling salesman problem. So the traveling salesman problem is one of those NP-hard problems, you know. So you have n cities with pairwise distances, and you want to find a route, shortest route that visits all cities. And that's a very hard problem if you have many cities. But Barvinok shows that even if you have many, many cities, you can solve it in polynomial time if this rank is small. So if you take the distance matrix for the cities, maybe there are many cities, but if the Barvinok rank is small, fixed, then there's a polynomial time algorithm. So that's why we call this the Barvinok rank. 2 is the Kapranov rank. So yesterday we talked about dead German mathematicians. So today we're going to talk about alive Russian mathematicians. Tomorrow too. So the Kapranov rank of M is the smallest dimension of a tropicalized plane containing the columns. Okay, so, well, this says, you can actually find, a tropical plane. Actually, this is equivalent, we'll see in a second. So this is equivalent to saying that you can take this matrix, you can lift it to a classical matrix of rank R. Okay? So this is the definition that sort of relates classical geometry. And maybe let's do this in characteristic 0. So it's good enough to take an algebraically closed field. And let's say M, let's say M has rational entries, so not to avoid, the entries should be in the value group. Okay? So in any case, if it lies in a tropicalized plane of that dimension, then it has that Kapranov rank. So Kapranov was also one of the inventors of tropical varieties. So he wrote a paper that was never published on the non-Archimedean amoebas. So I don't have much time to go over the whole history, but he stated the fundamental theorem for hypersurfaces without proof. So he was the first to state, in an unpublished paper, he stated the fundamental theorem for hypersurfaces. He didn't give a proof. He said it's obvious, And then I stated, in the Gröbner version, I stated it for arbitrary varieties. I wrote a book called Solving Polynomial Equations. And I stated it with initial, Gandiel contains no monomials, also without proof. Then David Spire and I, we gave a proof in the general case, the paper called the Tropical Grassmannian. But then there was a little gap. Somebody found a little gap. And then suddenly many people said, Spire Sturmfels has a gap. So many people, wrote papers. And they came up with different proofs, which is very nice. So there are different kind of proofs now of the fundamental theorem. But Kapranov was the first to sort of saw, what made a statement. And finally, 3, the tropical rank. We call the tropical rank of a matrix is the size of the largest non-singular square submatrix. Okay, that's another reasonable definition of rank. You have some big matrix, and then you look at the largest square submatrix that's non-singular, and that's the rank of the matrix. And non-singular here means it doesn't lie in the tropical hypersurface of the determinant. Okay? So non-singular means that the assignment problem has a unique solution. Right? So you have a big matrix, right? You look over all square submatrices. Every square submatrix gives an instance for the assignment problem for jobs and workers. And to be non-singular means that the assignment problem has a unique solution. Question? Yes, that's the topic of this lecture. Yeah, so the question was, is there a relationship between these notion of rank? And that's going to be the topic for our discussion in the next 49 minutes. Okay? But first of all, these definitions make sense, right? So in classical, undergraduate linear algebra over a field, these are all the same. Right? So if you have an ordinary matrix over a field, these notions of rank, they're obviously the same. But we're going to see here that there are some interesting differences. Okay? So just to illustrate, let's see an example. So simple example. Let's take this matrix, 0, 4, 2, 2, 1, 0, 2, 4, 3. Okay, so I claim that this matrix has rank 2 in all 3 definitions. So this is a 3 by 3 matrix of rank 2 in every definition. And so let's simply go through the definitions. So just make sure. So first of all, the Barvinok rank, well, the Barvinok rank is not 1. This is not a rank 1 matrix, right? So for instance, 1 times 3, well, that's a bad example. 2 times 4 is 6. 2 plus 4 is not the same as this. So this is not a rank 1 matrix, but it's a rank 2 matrix because it's 0, 2, 0 times 0, 4, 2 plus 3, 0, 3 times 2, 1, 0. Okay, so it's the sum, the tropical sum of 2 rank 1 matrices. You multiply this out, and that's the matrix. Now, it has Kapranov rank 2. Well, so here's because you can put it on a tropical line. So here's a line, that's a tropicalized line. And these points are collinear, right? So if I take the columns, so 0, 2, 2 is here, 2, 0, 3 is here, and 4, 1, 4 is here. So that's a line. And the projective plane, so this has Kapranov rank 2 because you can put them, they're collinear points. The columns are collinear. Question? No. Right? So that's Kapranov rank is 2. Now the tropical rank is 2. Well, the determinant of this matrix, so this is M, the tropical determinant is 4, and that's attained twice. Right? So the optimal value of the assignment problem is 4, but there are 2 solutions. So there's, let's see, 4, 0, 0, that's 4. And then we also have 3, 1, 0. Okay? So that's a singular matrix. So therefore, the rank, this is in all 3 definitions, that's a rank 2 matrix. Okay, so we have the following theorem today. So for every matrix, M, we have the following inequalities. The tropical rank of M is less or equal to the Kapranov rank is less or equal to the Barvinok rank. Okay, so we have this chain of inequalities, and both inequalities can be strict. Okay, so that's the theorem, and I'm going to explain this theorem. Okay, so the tropical rank is the smallest, the Barvinok rank is the largest, and the Kapranov rank is in the middle. It's too bad that the Kapranov rank is the largest, right, because of this complexity result. As I said, if we can if we have low Barvinok rank, then we can solve the traveling salesman problem fast. But it's hard to have low Barvinok rank. That's what this says. Okay. After all, complexity is hard. Okay, so that's the theorem. Let's discuss. So I'm going to discuss the 3 notions of rank, and I'm going to give you some ideas of the proof. Okay? So the first point is the following lemma. So let's discuss the Barvinok rank a little bit. So lemma. So for a matrix, so the first thing I'm going to do is I'm going to discuss this inequality. I'm going to show that this can be strict. Okay? So for a matrix M, let's say it's a D by N matrix, the following are equivalent. So TFAE, the following are equivalent. So first condition, M has Barvinok rank at most R, and 2, the columns of M lie in the tropical convex hull, lie in the tropical span. Okay? Tropical span, which we call the tropical convex hull, of R points in d-dimensional space. Okay? So here we can see this example. We have 3 points, but they're in the convex hull of only 2. Right? So they're in the convex hull of this one. The third point is in the tropical convex hull of 2 of the points. So therefore, the Barvinok rank is 2. Right? So on the other hand, if we look at the following matrix, so here's an example. Take the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Let's take this matrix. This matrix has Barvinok rank. Okay, so this proves this inequality, if you think about it for a moment, right? Because so this says that the columns, if you look at there are R, so there's R points that contain this in the column. So form the matrix. You make the matrix out of these R columns, lift them in any way, to the power series field. Look at the corresponding linear space. It will going to contain these columns. So this in particular implies this inequality, but also shows that it can be strict, because this matrix, this 3 by 3 matrix, has Barvinok rank Barvinok rank 3, but Kapranov rank 2. Well, why is that? Well, if you draw the corresponding configuration, right? If you draw the configuration, then the points look like this. So these 3 points, they're collinear. They're collinear, and therefore the matrix has Kapranov rank 2, but it has Barvinok rank 3 because no 2 of them contain the third in the convex hull. So this is a 2-dimensional polytope that's not spanned by 2 vertices. Right? So it doesn't suffice to have 2, to contain the third. And therefore, this is an example that shows that the second inequality can be sharp, and the color coding is exactly the same as in the last lecture. Okay, so that's Kapranov rank versus Barvinok rank. So now let's talk a little bit more about Kapranov rank. So here's another lemma. Here's a lemma that concerns the Kapranov rank. For a matrix M, which is a D by N matrix, the following are equivalent. First, M has Kapranov rank at most R. Two, M lies in the tropical determinantal variety. So it lies in the variety, tropical variety, defined by the r plus 1 times r plus 1 minors of a general matrix, right? So we know that if you take a general matrix, Professor Ahn knows, many others, right? If you take the minors of a matrix of a given size, they generate a prime ideal, has a very nice Grobner basis, you know. So you look at the prime ideal generated by the r plus 1 times r plus 1 minors, and then to be in the tropicalization of this variety means to have, for a matrix, means to have rank at most r. And the third condition is M is the valuation of a matrix. I'm going to write like this. F of t, it has a lift. Right? So where f of t is a d by n matrix of classical rank at most r. You can lift it to a matrix of rank r. Right? So we've practiced. That's exactly what we practiced. We practiced, and sometimes we win a brownie, right? So I give you a matrix, and the question is, can you find, you know, a matrix upstairs that has that valuation and has low rank? Okay? So those three conditions are equivalent. Now let me actually prove the two inequalities. So I said this was easy. Let me actually do this carefully. I'm going to prove this inequality, and I'm going to prove this inequality. We have enough time. This lecture is kind of a slow lecture. Let's do this, okay? Let me prove to you, that the Kapranov rank, the K rank of a matrix is less or equal to the Barvinov rank. So just that we can go over the concepts. So suppose M is a matrix of Barvinov rank R. I want to prove to you that the Kapranov rank is less or equal to R. So what does this mean? So this means that M can be written as a tropical sum M1 up to MR of some other matrices where each MI has rank 1, has tropical rank 1. Now for a rank 1 matrix, it's very, very easy to lift. If you have a tropical rank 1 matrix with entry, say, Aij, you can lift it by just writing T to the power Aij. So if you have a rank 1 matrix, you can trivially, you know, lift it to a classical matrix of rank 1. So let's do that. So find matrices. They exist easily. Matrices Fi upstairs, so over any field with the valuation of rank 1. And we can arrange it in such a way, I claim we can arrange it in such a way that the valuation of F is M, where F is the sum of these Fi. So how do we do this? Well, so Fi is simply the trivial lift of Mi. So I simply take, you know, each entry and I raise it to that power. But then I multiply the coefficients just by distinct numbers, by general numbers. So that when I add up these matrices, there's no cancellation, right? So each of these matrices Ai, every entry is a monomial. And I can be free to choose the coefficients at random, right? And it's an infinite field, right? It's algebraically closed, let's say. So there's enough constants around. So I can arrange for this sum to be without cancellation. And then it follows, you know, since it's cancellation free, the value of F in every coordinate is equal to M. There's no cancellation, so therefore this implies that. So no leading terms cancel. But you know, F is a classical matrix, right? So since the rank of F is at most R, I mean, I've written it as a sum of rank 1 matrices. So the rank is at most R. It follows that the Kapranov rank of M is at most R. And that's exactly what I wanted to show, right? To show that the Kapranov rank is at most R, according to this lemma, I need to exhibit a matrix upstairs with the correct valuation of rank at most R. So that's the proof of this inequality. Now let's prove the other inequality. Let's prove that the tropical rank is less or equal to the Kapranov rank. So the T rank is less or equal to the K rank. Okay, so let R be the tropical rank of M. So I'm going to use now the second characterization. Okay? So M, I'm going to take the definition. So R is the tropical rank of M. So remember, the tropical rank is the largest size of a non-singular submatrix. So M has an R by R minor for which the assignment problem has a unique solution, which is not in the tropical determinant hypersurface. Now what that implies is for any lift, f of t of M, the corresponding minor upstairs must be non-singular. Right? If you have a non-singular tropical matrix, every classical lift must be non-singular. Converse, so that's equivalent, right? So if I take a classical singular matrix, its tropicalization downstairs is singular, right? Why is that? Because lowest order terms must cancel. If I have a classical matrix with entries in a field with evaluation, if the determinant is 0, right, I write out the terms, all n factorial terms for every assignment of jobs to workers. In order for the determinant to 0, there must be, lowest term cancellation. So therefore, a classical singular matrix, its tropicalization, must be tropically singular. Contrapositive says, if I have a non-singular tropical matrix, every lift must be non-singular. So in particular, that lift must be non-singular. So therefore, in any lift whatsoever, the rank of that minor is at least R. So therefore, the rank of the big matrix is at least R. But that says, that the Kapranov rank is at least R. Okay. Right. So if for every, so what I've shown is I have a matrix of tropical rank M. For every lift, the rank is at most R. So there is no lift of rank R minus 1 or less, right? There's no lift of rank at most R minus 1. So therefore, it's not the case that the Kapranov rank is less or equal to R minus 1. So therefore, I get the correct inequality. So I have a matrix of tropical rank R, and I've shown that the Kapranov rank is at least R. Okay, so that's good. So we're almost done. I've almost proved the theorem. All that I need to show is that this inequality can be strict. Now that turns out to be the hardest. That's the hardest part. That's so hard. For that we need matroids. Okay? For that we need some hard stuff called matroids. But so far, everything was sort of pretty straightforward. Okay? But before we get there, let me ask you one question. So here's the audience participation question. how do you compute the Kapranov rank of a matrix? Can you give me an algorithm for computing the Kapranov rank of a matrix? Let's keep this up, actually. Right? This is our inequality. Now, in fact, for all of these, right? So what are the algorithms? So the question is, how would you compute? How would you compute the Kapranov rank of a matrix? Okay, so suppose I give you an 8 by 8 matrix and I ask you to calculate the Kapranov rank. Well, these other ranks, that's a little tricky, you know. So, but for the other ranks, you sort of know how to do it. So how would you calculate the Barvinok rank? Well, for the Barvinok rank, you take the tropical convex hull of the columns. Right? So there's the tropical convex hull, and then you check whether you can leave out, you know, how many, you know, for each point you leave out. You just look at the vertices of the tropical convex hull, and then, you know, how to remove, you know, redundant columns, and then however many is left, that's the Barvinok rank. For the tropical rank, here's a stupid algorithm. So I'm not saying that these algorithms are efficient. You know, there's some open problems about the complexity and so on. But here's a stupid algorithm for computing the tropical rank. Well, look at every square submatrix, right? Solve the assignment problem, and check whether the solution is unique. Right? That will tell you the tropical rank. So that's a big, you know, that's sort of not so clear how you would do this in polynomial time, but at least in principle, that's an algorithm. Okay? Now, what about the Kapranov rank? So let's say I give you an 8 by 8 matrix, and I ask you to calculate the Kapranov rank. So how would you actually do this? Well, it's kind of the Brownian problem, right? And one way to approach this is to use this approach, to say, what's the smallest rank of a lift? You look at sort of all possible lifts, right? You get, you know, -3 plus t. You be very clever. You look at all the possible lifts, and then among all lifts, you pick the one of lowest rank. So that would be one approach to do that. It's going to fail. I promise, no matter how large a brownie I offer, you will not be able to get it. It's very, very, very difficult to actually explore all the lifts. So that approach, I think, is not the right approach. The right approach is this approach, to use this method to test for the Kapranov rank. Grobner bases are your friend. Whenever you can reduce a question to Grobner bases, do. Right? So if I give you this 8 by 8 matrix, how do you calculate the Kapranov rank? Well, you make a ring, you look at the, let's say you want to test whether the Kapranov rank is less or equal to R. So you want to test, you know, whether M lies in this tropical determinantal variety. Well, you make a list of all these minors, and then you calculate the initial ideal with respect to the partial term order M. You make a partial term order with weights M. Let's call this ideal something, right? So you calculate the initial ideal of this with respect to these weights, and then you check whether this ideal contains a monomial. And if it contains a monomial, then it's not in there. If it doesn't contain a monomial, then the rank Kapranov rank is at most R. So this is the way to go. Okay? So this is how you calculate the Kapranov rank, is you just check whether the matrix lies in the determinantal variety. Now, what else? That's interesting. I see. So that's good. So I Xeroxed this from some other lecture notes. And the other lecture notes had 3 pages, 1, 2, and 3. And I just realized I Xeroxed page 2 twice. So I have no page 3. So I just have to tell you the rest of the story without any notes. But that's okay. We can do without notes. Okay. So Now, the other remark may be, if we talk about the tropical, let's talk about the tropical rank. So here's another lemma. So M has tropical rank R. So I want to understand this inequality, the difference between tropical rank and Kaplanov rank. So N has tropical rank at most R if and only if M lies in the tropical determinantal pre-variety. In the tropical determinantal pre-variety that you get by intersecting the tropical hypersurfaces corresponding to all minors. So if you look at all the minors, and for each minor separately you form the tropical hypersurface, and you intersect those tropical hypersurfaces, then you get a pre-variety. Now that pre-variety contains the tropical variety. So this contains the tropical variety, but they may or may not be equal, right? So they're equal. So they're equal. So therefore, corollary. So let's go without notes. So corollary. Equality holds. So this left equality holds. For all. So I want to argue for all tropical matrices of rank, all matrices of tropical rank R. So let me say holds in rank R. So holds in rank R. So what I mean by that is holds in rank R. I mean if this has rank R, then that has rank R. Right? So holds in rank R if and only if the R plus 1 times R plus 1 minors form a tropical basis. Or form a tropical basis. So the issue whether Kaplanov rank and tropical rank are equal has to do whether the minors of a given size form a tropical basis. So if the analogy is now clear, right? So to the Grassmannian is quite clear. So rather than looking at the minors, you look at the three-term Plicker relations, then tropical rank is to Kaplanov rank like Dressian to Grassmannian. Right? So the relationship between the Grassmannian and the Dressian is exactly the relationship between tropical rank and Kaplanov rank. So tropical rank and Dressian, they're combinatorial concepts. They're relaxant. They're combinatorial relaxations. So tropical rank to Kaplanov rank is like Dressian to Grassmannian is like matroid to realizable matroid. Right? So there's a geometric notion that's hard to capture, but in combinatorics we can relax it and go to things like matroid and tropical rank. So tropical rank is a combinatorial relaxation of the hard geometric notion of Kaplanov rank. Okay? So in this paper, so this lecture is based on a paper with Santos and de Vellin on ranks of matrices that we wrote a couple of years ago. And in this paper we showed that under certain circumstances this is actually the case. So there are some results. So this is true. This is true for 3 by 3 minors. So if the rank is 2, so if we look at 3 by 3 minors, so the 3 by 3 minors of any matrix, they form a tropical basis. There's a construction, and it's a very beautiful space. So if you take the 3 by 3 minors, so then you get this tropical variety of matrices of tropical rank 2. And that's a very, very beautiful variety. So the combinatorics is very well understood. There's a nice new paper by Yu and Markvik where they give a shelling. So they shell this space. They determine the homology. So again, it's one of those spaces where everything is known. So 3 by 3 minors, we know everything. It's also okay for maximal minors. So maximal minors are also okay. So if you take any matrix, so let's say, for instance, you have a 4 by 6 matrix, and you look at the 4 by 4 minors, right? So that's the 4 by 4 minors. They form a tropical basis. So there it's also okay. So there we have the inequality is also an equality. Okay? On the other hand, there's a counterexample. So let me give you a counterexample. And the counterexample goes like this. Something like 1, 2, 4, 2, 3, 5, 7, 6. Okay, so there's the Fano plane. So now we're going to do the following. So this is a general construction. So the general construction for if you have a configuration like this in the plane, you make a matrix whose rows are the points and whose columns are the lines. So in general, for a matrix, for a matroid, the rows are the points and the columns are the co-circuits. Okay? And then you write down the 0, 1 incidence matrix. You simply write down the incidence matrix. So the first line is 0, so 0, for instance, 0, 0, 1, 0, 1, 1, the other way, I'm sorry, it's this instance. 1, 1, 0, 1, 0, 0, 0. It's going to be a 7 by 7 matrix. So like this. And then you go 1, 1, 0, 1, 0, 0, and so on. Cyclically, you shift it through. Okay, so this is the matrix. Now, this matrix, this 7 by 7 matrix, so this has tropical rank three, but it has Kapranov rank 4. Okay? And there's an analogous construction coming for whenever you have a non-realizable matroid, so this is not realizable in characteristic 2, you can build such a matrix whose Kapranov rank is bigger than the tropical rank. Well, how can we check this? So suppose you don't know anything. You want to check this from first principles, right? So how do we check that the tropical rank is 3? Well, you check that. You pick any 4 by 4 minor, right? So pick any 4 by 4 submatrix, not necessarily, consecutive, and you check that the minimum is attained twice, right? So you can run over all 7, choose 4, times 7, choose 4, right? Less than 5,000 matrices, less than 500 matrices. You check all 4 by 4 minors, and you check that they're tropically singular, and that verifies that the tropical rank is 3. Okay? On the other hand, the Kapranov rank is 4. How do we check that? Well, we go to Macaulay 2. We make a polynomial ring in 49 variables. We specify the term order to be that. Right? That's our term order. Those are the weights. Then we write down the prime ideal of 4 by 4 minors. We calculate the initial ideal, and boom! There's a monomial in the initial ideal. Turns out there's a monomial in there. Happens to have coefficient 2, but 2 is not 0, so we're okay. So there's a monomial in the initial ideal. So therefore, the Kapranov rank is bigger than the tropical rank in this example. Now, that's almost the end of the lecture. So I've gone, over time in some of the lectures. So I have a few remarks to close, but maybe this would be a good moment to pause for a question. Okay, so we have these three notions of rank. We have a, and philosophically they correspond to different areas of math, right? So the largest notion of math, the largest notion of rank, the Parvinov rank, that sort of corresponds to complexity theory, theoretical computer science kind of discrete math. The smallest notion of rank, tropical rank, corresponds to geometric combinatorics, polytopes, that sort of thing. And then the middle one, the Kapranov rank, corresponds to algebraic geometry. These are actually, those that you can lift to matrices over the field. Any questions? Yes.
We have a single matrix which has both inequalities.
Yeah, you can make it. I think you can you can take this matrix and then combine it with the other matrix somehow, Make a block matrix with infinities outside, So yeah, you can combine. And these can be arbitrarily big, So the differences can be arbitrarily big. Well, if there are no further questions, then why don't I say a few words about the exercises. So then we can have an early lunch, but we can meet at 1 o'clock, those of you who want to discuss and maybe look at these exercises. Let me just quickly run through. So do you have them? This is called Exercises for Discussion on Thursday, Friday, and Beyond. Okay? So there are two exercises that relate to this lecture we just heard. So one of them is lecture 5. It says, in your opinion, is the following statement true or false? The 4x4 minors of a 5x5 matrix are a tropical basis for the ideal they generate. And it turns out that's the smallest open case. So that's an open problem. So I don't know the answer. And it's a tantalizing problem. So several people have tried to solve this. And there was a paper on the archive by Roubaix last year where she claimed to have answered it completely. So ultimately you want to have a theorem that says, tropical rank equals Kapranov rank if and only if R, D, and N satisfy the following. Okay? So she had a theorem, but there's a gap in the theorem. And the decisive case is this case. So this is actually an open problem. We don't know that. And the reason, sort of the philosophical reason is, we don't know whether matroid theory is the only obstruction for this difference. So whenever we have a non-realizable matroid situation, we can create this inequality. But we don't know whether there might be other obstructions, whether there might be other ways of forcing the inequality. And we don't know in this case. So this is actually an open problem, but I just put it on there, so you can think about this, how you would approach this. Maybe you have an idea. Number 6 is kind of a little example to review, convex hull. So it's a nice little matrix, right? You look at this matrix, and it has pretty low rank classically, right? Looks like a very degenerate matrix, but that's actually a rank 3 matrix. And this shows something very nice. This exercise, I didn't cover this in the course, but there's a remarkable fact in tropical math, which is crucial for the LFD spaces. Crucial, crucial, crucial. If you have a matrix, suppose you have a rectangular matrix, okay? The following is true. The convex hull of the rows equals the convex hull of the columns. That's shocking, Now, usually you only know that the rank is the same. You have a matrix, right? You have and the row rank equals the column rank. But that's all you can say. Otherwise you can't say so much. But in tropical geometry, the tropical convex hull, which is a polyhedral complex, is isomorphic, is piecewise linearly, is isomorphic to the convex hull. The row convex hull is equal to the column convex hull. And this is a little example to illustrate this. So you can try it out. So this is the columns. They give you a hexagon, tropical hexagon in the plane. The rows, they give you a tropical triangle in 5 space. But the tropical triangle in 5 space is the same as the tropical hexagon in the plane. It's a bit counterintuitive, but you can play with this and you can check it. The last problem, 7, relates to the first lecture tomorrow. Actually, to both lectures tomorrow. It's a little example of a curve. It's an elliptic curve realized in the blow-up of a P2 at 3 points. Nice reflexive polytope. And I'm going to talk tomorrow about curve counting, Mikulkin's curve counting theorem. So Gromov-Witten invariance. So this is a little example to kind of warm up to curve counting and discriminants. And then what else? So problem 1 is just the counting, you know, how many, so you have a tropical arrangement of hyperplanes, you know. So people study sometimes hyperplane arrangements. So here's an arrangement of tropical lines. So the complement, you know, of this arrangement is a finite union of polygons, open polygons, and the question is how many are there, you know. Number 2, so in tropical geometry we have an inverse problem. Just like in Galois theory, we have an inverse problem. And the inverse problem goes like this. So if you have a tropical, suppose you start with the classical variety, you tropicalize it, what do you get? You get a pure, strongly connected, balanced polyhedral complex, or fan. But is the converse true? So suppose we have a pure, you know, balanced, whatever, you know, strongly connected, with rational slopes, polyhedral complex. Can you find a variety, classical variety, that has that tropical variety? Okay? That's what I mean by the inverse problem. And in general, the answer is no. And the counterexamples are quite delicate. But sometimes the answer is yes, and the answer is yes for curves with trivial valuation. So if you have, the statement is you have a field with a trivial valuation, you have any arrangement of rays. You have any bunch of vectors like this in any dimensional space, as long as the vector configuration is balanced, you can realize this by a curve. And the hint was given in the first example this morning. You know? Number 3 is a secant variety situation. So there is the first secant variety of the rational normal curve. So this is something. So all the people who know about NP and secants and syzygies and so on, you know, you got to do this one, right? So this is the variety of secant lines on the rational normal curve in P4. How easy can it get? Okay, and then the tropical picture. Number 4 is Bernstein's theorem. So some of you know this theorem. If you have two polynomials in, say, in 2 variables, then the number of roots will be the mixed area. This is really a theorem in tropical geometry. And so if you've seen that before, this might be a good opportunity to review it this afternoon. So that's it. So I'll see you at 1 o'clock.